I've done this before. But, sometimes you just got to redo things and start from scratch again. And I'm going to show you how to solve physics problems, a physics problem, using numbers. And this is a numerical calculation. And of course, I'm going to use something that looks a lot like Python. That's technically not Python. And at this point, what should you know coming in? I don't think you should know any programming. I don't expect that. I think you should have, at least some introductory physics. And I think you can do it. I believe in you. Let's just get started. So here I have a tennis ball, and I don't even know the mass. I'm going to say it's 200 grams, so 0.2 kilograms. And if I'm going to release it from a height, h, let's say 2 meters above the ground. And it's going to, with the initial velocity, we'll call that v1 in the y direction of 0 meters per second. And I'm going to solve this problem like you normally would. And then I'm going to look at a different problem that's harder. So if I have a ball, I know that there's a gravitational force in the y direction. I'm going to use the y direction, one-dimensional problem. So I'm not going to write these as vectors, although we could. It's not so hard. But let's just start baby steps, right? Gravitational force. I can write down Newton's second law, F net is mass times acceleration in the y direction, That's the only force. So I have, actually that would be negative mg in the y direction. It's going to be equal to ma, and that's the y acceleration. Well, the masses cancel, and I get a equals negative g. And if I have an object with a constant acceleration, I can find out how long it takes to hit the ground or whatever I want using the kinematic equation, which I'm not going to derive. Hopefully you've seen this before. y2, the final y, is the initial y plus the initial y velocity, which I'm just going to call 1 times t minus 1/2 g t squared. So let's say we want to find out how long it takes to get to the bottom. I'd solve this for t. I'd say y2 is 0. y1 is h, v1 is 0, so I have minus 1/2 g t squared. I can solve for the time fairly easily. Add that term to both sides. 1/2 g t squared equals h. T equals the square root of 2h over g. And that's going to be meters divided by meters per second squared. It does give me units of seconds. So that's that. Now you may be thinking, where's the Python? Where's the numerical calculation? I get it. I just want to do this and then set up another problem, and then I'm going to solve this numerically, and then we'll solve the other one numerically. Now what if I change this problem? I have the same thing. I also have a height of 2 meters. And I'm going to drop something from rest, so v1 equals 0. You notice I'm like leaving it blank what I'm dropping because it's going to be a coffee filter. This coffee filter has a mass of, I don't know for sure, but I'm just going to say it's 1 gram, which I think is pretty heavy. It's probably too heavy, but that's fine. 0.001 kilograms. That's 1 gram kilo. Yeah, that's right. So what's different here? If you've ever dropped a coffee filter, you know it's going to take less time. I mean, more time than it takes for a tennis ball to drop from the same height. Because now we cannot ignore air resistance. And at some point down here, we have the gravitational force pulling down. We have the upward drag force, Fd. And that's what makes this a difficult problem. And then on top of that, if we say it's a v squared drag force, I can model the drag force, put it right here, F drag as 1/2 rho A C v squared, where that's the density of air, that's the cross-sectional area, that's a drag coefficient, and that's the velocity. And if I put that together with this, I get Newton's second law. That's an upwards pushing force, 1/2 rho A C v squared minus mg equals ma. Now we have a problem. We have a problem because I can't get an expression for the acceleration like I did up here. The acceleration depends on the velocity. So this equation assumes a constant acceleration, which we totally do not have. So you can solve this problem actually, but not without using differential equations. And even then, there's some situations where it doesn't work, but you can solve it. So, but we can solve this using just basic physics. Let's go back up to this problem, and I'm going to resolve it. I'm going to put in my values, and then I'm going to solve it a different way. And then we can model that in Python, and then we can come down here and model this. 'Cause we want to model this one first to make sure it works. And if this takes an hour, it takes an hour. We're going to sit here until we get it right. So let's go back over here. I've already solved that problem once. I actually can trace this. Look at that. H equals 2 meters. And you'll notice I haven't even touched Python yet. V1 equals 0 meters per second. And I found that T was the square root of 2H over G. That's right? Yeah. Let's put in our values there. So the mass didn't matter. So we'll put in our values. It's going to be the square root of 2 times 2 meters divided by 9.8. And I'm going to put that in my calculator. See, no Python. Clear square root 2 times 2. Why did I just do 2 times 2? I know what 2 times 2 is. Divided by 9.8 equals 0.639 seconds. Okay, so we already did that problem. Now let's do it again. What if I, instead of letting it fall all the way, I let it fall just a short way right here. So it's down there, and it got smaller, and it shouldn't get smaller, it should be the same size. What if I want to find out how fast it's going and where it is after a time interval, I'll call this delta t, of 0.1 seconds. So after just a tenth of a second, it's going to take 6/10, almost 7/10 to get there, but this after 1/10 of a second, where would it be? Well, we know the definition of velocity, we know the definition of acceleration. So I know the acceleration is negative g. We already know that. We got that from Newton's second law. That's a given. I know that in the y direction, I can define acceleration as the change in velocity with respect to t. That's true. That's how we define it. It's a delta v over delta t. Well, what if I have delta t of 0.1 seconds? Well, then I can write this as, now I'm not going to call this v2. I'm going to call this v something else. So v2 is going to be the velocity right here. I can write this as v2 minus v1 over delta t. That's true. Nothing. I haven't cheated yet. You notice I said yet, because you know I'm going to cheat. And I want to solve this for v2. I can multiply both sides by delta t. I get v2 minus v1 equals a delta t. And then I can add v1 to both sides. I get v2 equals v1 plus a delta t, where a was negative g, but I'm going to leave it like that. It's fine. So if I want to find it after delta t of 0.1 seconds, I just need to know the starting velocity, the acceleration, and I just calculate it. We can even do this. Let's do it. Clear. So 9.8 times 0.1, which again I didn't have to do, plus 0. This is negative 9.8. So I get v2 is negative 0.98 meters per second. If I want to find the next time interval, v3, I could do the same thing, right? I'd just say, well, v3 would be v2 plus a delta t. v4 would be v3 plus a delta t. So really, this equation works for any sets of i's, right? If I know the velocity at the beginning of the time interval and I know the length, I can find the new velocity. So it's kind of cool. We can call this velocity update. What about the position? Well, let's do something here. What if I say the velocity is defined as the change in position y with respect to t? And I'm going to use delta t of 0.1 seconds. Well, this is y1, and let's call this y2. So y2 minus y1 over delta t. And if I solve this for y2, I multiply both sides by delta t. y2 minus y1 is v delta t. And then add that to both sides. y2 equals y1 plus v delta t. But now we have a problem here that's different than over here, because if it's going from here to there, what's v? Technically it should be the average velocity. This should be the average velocity, and then it works. This is the average velocity if the acceleration is constant. But if it's a 0.1 time interval second, then I can just use this velocity. I'm going to use actually v2. I'm going to use the velocity at the end of the time interval. It's wrong. Wrong. But if it's only partly wrong, it's partly right. That's important, right? Let's just go ahead and find what this is. So I know that's at y1 is 0, v2 is 0.98, delta t is 0.1, so y2 is going to be equal to, oh, y1 was h. I'm sorry, y1 is not 0. y1 is h. So it's going to be 2 minus 0.098 meters, which would be 1.802. Sometimes just like, I think that's right. 2 minus 0.098 equals, yeah, 902. That's the wrong answer. I just want to make sure that that's clear. That's the wrong answer, but it's only kind of wrong. So what if I want to find the next position, y3? Well, I can do the same thing. I can say y3 equals y2 plus v3 delta t, and I can find v3 over here. So you can kind of see what we're going to do here. We're going to break this problem into short time intervals, and I'm going to use this to find the new velocity at the end of each time interval. I'm going to use this to find the new position at each time interval, and then I'm going to go to the next one. So in this case, if I want to get all the way down to the ground, I'm going to have to do this like 6 or 7 times, right, before it gets down to there. And that's fine. But I don't want to do that on my calculator. I want to do it a smarter way, and so I'm going to use Python. So let's jump over to the computer. We're going to use Python. Don't worry. It's not a big deal. I'm gonna show you everything you need to know. I don't assume that you've seen anything in Python, and that's completely fine. So here we are, and I will give you a link to this code. This is not technically Python. I'm using Trinket.io with GlowScript, and this is an online implementation of Python. And it has some other stuff in there too. So this is what I would recommend you use. So you don't have to install anything. You can share the code with other people. It's going to be great. So let's just get started. You're required to do the following: print hello world run. So you can type your code right here. You click run and it runs it. Hello world. Not everyone does that. So you did that. If you did that, you're a programmer right now. Note: do not change this line right here. That is used by the software to make sure that things are working correctly. In Python, we can make variables. So I'm going to say a variable like this: h equals 2, print y. It's going to print 2. So I assigned the variable y to be 2, and I printed it. Now, if I did this, 2 meters, I want it to be 2 meters, then I get this, an error. Because it doesn't know what that is. If you write a number, Python's like, okay, it's a number, I got that. It's an integer or a decimal, I don't really care. It can deal with it. But when you put 2m, it's like, I don't know what m is. So we don't do units in these numerical calculations. We just deal with numbers. And some people may call these computational physics problems or computer problems, whatever. I like numerical because you don't actually have to use a computer. You're just number-based. Now we can do some operations with this. I could print, let's print it. Oh, let's do it like this. X equals y times 2 plus y squared minus 3. It's a stupid thing, but I'm going to do it anyway. And now I'm going to print x. And so it did that. Okay, so we can do all these operations. If you're not familiar with the operations in Python, I'm going to go through it as we do that. Let's put in all our other variables that we're going to have here. We have our acceleration is going to be, I'm going to call it a. Let's do it this way. G equals 9.8. A equals negative g. That's the way we really had it. V equals 0. I released it from rest. And t equals 0. dt equals 0.1. Now, you may notice something already. I put y is equal to 0. I put v is equal to 0. I didn't say y1. I didn't say v1 because we don't need to do it that way. We can just change our values. Let me make this a little bit bigger. That looks a bit better. And that's kind of the magic of numerical calculations, is that we don't need 6 values for y. We can just keep changing it. Now, let's just manually put in our calculations for that one step. I'm going to show you how to do this. So first I want to find the velocity at the end of the time interval. So I'm going to write this. V equals v plus a times dt, just like I said before. I'm going to print that out. And then that's the same thing that we got before. Now, in the print statement, I'm going to jump ahead here. You don't have to do this, but I could put v quote equals comma v comma quote meters per second if you want to make it look nice. And sometimes we do. So printing's really easy in Python. That's nice. Now, you should be looking at this and saying, what the heck just happened? That's whack. Shouldn't the v's cancel? If I have v equals v plus a delta t, the v should cancel. And it should, except it doesn't, because it doesn't do that. This is not an equal sign. I know it's an equal sign, but it doesn't mean equal. It means make equal. It tells the computer to take the value for v, which is 0, take the value for a, which is negative 9.8, multiply it by dt, 0.1, add those two together, and then set that to the new variable. So it changes the value of the variable. So if I print v right before that, it'd be 0. Right after that, it's negative 9.8. So that's really nice. I don't need to keep up with all that stuff. Now we can do the same thing for y. Y equals y plus v times dt. And then I can print y also. And I'm going to do something else. Y. I'm going to do nice. I'm going to print the time. I'm going to update time. I didn't talk about that before, but after I do those, I want to have a new time, right? So time should be 0.1 seconds. So let's print the time. And let's run this. There you go. Now I can do it again, right? Let's just do it again. I'm going to just do this the nice way. Copy that. There's nothing wrong with this. Paste, 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 paste. So I have a bunch of, I'm doing those things a whole bunch of times. Let's just see what happens. So I had v, y, t, and I want to look down here until it hits the ground. So I'm getting at y 0.5. Y is negative 0.058. Look what happened right there. So sometime between t equals 0.5 seconds and t equals 0.6 seconds, it hit the ground. And it's going negative 5.8 meters per second. So that's fine. Now, if I want to break it into a smaller time step, it's going to be a problem to copy and paste that much stuff. So I don't want to do that. Here's another way to do this. We're going to use a loop. And this is when the real programming happens. So I'm going to just copy all this, except for the first one. Okay, I just have one again. Now what I'm going to do is a loop. And this is going to be kind of weird if you haven't seen it before. It's fine. Let's just do while t is less than 0.5. That's the best way to do it. So in Python, we make a loop with some conditional statement. This is while t is less than that value, which it is at 0. And then we put a colon. And then everything in the loop has to be tab indented. So I can indent all that. And this will keep doing this until t is no longer less than 0.5. Let's just run that. So you'll see it printed it out a bunch of times. It's the same stuff that we had before, but it's with a lot less code. And we still got down to y is 0.53, t is 0.5, so that's fine. But let's not print that out every time. If I dedent it, whenever it gets to the end of the loop, then we'll do that stuff. Okay. I want to jump right ahead and make a graph. And I know it's a lot right now, but we don't want to keep printing out all this stuff. So I'm going to make a graph. I'm going to make the simplest, easiest graph in the entire world. All I have to do up here is say f1 equals g curve. And we can make fancy graphs later. So if I do that, nothing happens. If I run that, they get the same thing. But if I plot a point on there, I want to plot a point every time I calculate the position. I want to plot position as a function of time. So what I can do down here is to add a point to the graph every time I go through the loop with this f1.plot, and then I give it the x value and the y value. So I want to plot t on the horizontal axis and y on the vertical, like that. And now we can start seeing some cool stuff. And there you see my trajectory. It's a little big, right? Because I didn't put any parameters in there. But there's my graph. I didn't do anything fancy. I didn't put any titles or anything. I am going to put titles just so because we're going to use this. So let's make this, skip this step if you don't want to. Graph, let's just do x title equals t, y title equals y. And here's the most important part. Width equals 500, height equals 250. It's going to make the graph smaller. Not small enough, apparently. Let's make it a little bit smaller. 400, 200. I guess I could zoom out a little bit. There we go. So there's my graph. Looks pretty nice. And you can see these data points right there. Right? You could turn that on so you could actually see it, but I want to make it as simple as possible. Now, we could do this another way. I could run this until y gets to 0 instead of t greater than this. I like the t because it always works, but be careful with this. What about while y is greater than 0? So this will keep doing it until it gets to the ground, which is what we wanted. And you'll see here I have a time of 0.6 seconds, which we already said was wrong. I had it says 0.639 seconds. And that's because I'm making, there's two reasons. One, I'm making that assumption that the velocity is constant during that time interval, which it's not. And number two, I'm breaking it into small steps. So when does it actually hit to 0? See, this doesn't even it actually went past 0. Well, we can fix that by making a smaller time step. What if I make that delta t of 0.01? I don't really have to change much, right? Now it's just going to take 600 loops instead of, or 60 loops instead of 600. If I run it now, you'll notice I get a much smoother curve, and the time of 0.64 seconds. I had 0.639 before. That's pretty good. That's really good. And then if I want to go even crazier, I can make that 0. Look at that. I get the same thing. So the smaller my time interval is in my calculations, the more true that velocity is constant works for during that time interval. But there's your first numerical calculation. Okay, now let's do a problem that you couldn't normally do, and that's solve a falling coffee filter. So I'm going to click this right here. I'm going to save it. My first coffee filter. I'm going to give you the code. It's going to be in the link down below. Let's go back to the paper and see what we need to do to change this so that we can use it for our falling coffee filter too. So here we are. Back to the coffee filter. I have this, and I need the mass of 0.001 kilogram. The density of air is 1.2 kilograms per cubic meter. The area, let's say the coffee, how big is the coffee filter? Let's say it's 0.5 by 0.5, so centimeters. It's not, but that's fine. So 0.05 squared meters squared. And the drag coefficient depends on the shape. I'm just going to pick 0.6, no units. So I still have this coffee filter, a height h. I still have the initial velocity of 0 meters per second. That's still 2. And my equation in the y direction, F net, will be 1/2 rho a c v squared minus mg equals ma. So I added this term in there now. That's that drag coefficient, which as the thing falls down, that's going to change. So in this equation, what I want to do is to find the acceleration. And I'm going to assume that that's constant. Before it was, this time we're going to assume it's constant. So if I divide both sides by the mass, I get A equals rho AC V squared over 2M minus G. Okay. Now I can again assume, this is not constant, but I can assume it is. So once I have that, I can find the second velocity, V2, equals V1 plus A delta T. And then I can find the new position, Y2 equals Y1 plus V2 delta T. So I can do all the same steps. The only thing different is now I have to calculate the acceleration. And the acceleration changes each time I go through that loop. So you see, doing a falling tennis ball and doing a coffee filter numerically is just one step different. And that's kind of nice. So let's just go ahead and modify our code to make this work. And it's going to be amazing. Back to the computer. Here we are. I'm going to put in some other values right here. That is no longer true. A is not equal to that. I do need the mass, 0.001. If you want to put in a comment, if you want to put the units, there are comments in Python. Use the as my kids would say, hashtag. It's the number sign, and I can put the units there, kilograms. It's your responsibility to keep up with the units. The human. I need density, rho is 1.2, A is 0.05, star 2. Squared in Python is star, not hat. Okay, I don't know why. It's just what it is. C equals 0.6. I got it. Okay. So then down here, before calculating the velocity, I'm going to calculate the acceleration. So I'm just going to write the equation I just said. A equals rho times A times C times V squared. V is, I need a V, right? V is 0, I know that. Divided by 2 times M. Be very careful about parentheses. If you're not sure about whether that should be a parenthesis there or not, put the parenthesis in there, right? Doesn't hurt anybody. And then minus G. And that's my acceleration. Now, this line calculates acceleration, updates the position, updates time. Everything's the same. Let's run this thing. It looks different. I have a different time. My final position's different too because it went a little bit past the thing. But that's pretty good. You'll notice one really great thing from this. Here, it looks like it's accelerating. Here, it's at a constant velocity. It's a straight line. That's exactly what you would expect. That's terminal velocity. That's what you would expect. And that's it. You did it. You did a numerical calculation. Great job. Let's just do something for fun. I want to plot two objects. I want the tennis ball and the coffee filter falling together just so we can see a comparison. And to do that, we're going to have to make two graphs. So let's call F1 the ball. And I'm going to make that a blue. And I'm going to give it a label. Ball. And F2 is G curve. Color equals color dot. If you don't like graphing, don't worry about it. This is not. You don't even have to make the graph to do a numerical calculation. Label equals coffee filter. That might be too long. Now I'm going to need two values for everything. So these are already for the coffee filter. So let's make another one. YB equals 2. I need VB equals 0. And the time I don't need. So, but I need to update the position and the velocity of the ball. I guess I need AB equals negative G. So those negative G. Those are all my values for the ball. Down here, I'm going to update the velocity of the coffee filter. I need to update the velocity of the ball to VB equals VB plus AB times DT. I need to update the position of the ball. YB equals YB plus VB times DT, and then that's it. And then I need to graph it, F2 dot plot. Oh, let's put that one as 2, 1. I don't know, it doesn't really matter. So that's the coffee filter, and this one's going to be T and YB. And let's run it. That's great. That's a great graph right there. Great graph, great physics. And that's a numerical calculation. And that was one of the simplest ones. You can do some other really great things. Mass oscillating on springs, really great. You can do things like model things in 3D. You can use vector calculations. You can do things in 3 dimensions. Vectors are built into GlowScript v Python. It's just awesome. I don't know what else to say about it, but I mean, I wanted to go through all the really basic steps here, just so you can see what happens in a numerical calculation and how you can set it up. And it's not super hard. And I'm going to save this, and try to do it from scratch. Don't look at the code. Look at just the video and type it, pause it and type it and stuff like that. You're not going to get great at numerical calculations until you do numerical calculations. But once you do them, once you get the hang of them, it gets better. And you can do a lot of great things. And and the programming isn't even that difficult. And that's what makes it so appropriate now, is that Python is so accessible, I think, compared to other languages. But you don't even have to use Python. You could do this by hand, right? And it wouldn't be too terrible. So there you go. That's your first introduction to numerical calculations. I'll probably do another video of the same thing in a year or two, because it's that important. But I hope you found this useful. Let me know if you have any comments. I'll try to answer your comments down below.